Welcome back to the OFDM lecture. So now we continue with the discrete Fourier transform, or DFT. So this is a Fourier transform of a finite sequence of samples. So we consider that we have n samples, so a vector of length n. And then the DFT is defined by a so-called DFT matrix. This is a unitary matrix of size n by n with these entries. So maybe it's good to do an example for n equal to 2, no, for n equal to 4, right? It will be 1 over 2. And then the first row will be 0, 0, oh, no, that's wrong. Sorry for that. 1, 1, 1, 1, 1, 1, 1. And then this first element will be e to the power minus j 2 pi 1 over 4. And then you can populate all the other entries in this matrix as well. The matrix is unitary, so this means that Q Hermitian Q is equal to an identity matrix is equal to Q Hermitian. Okay, and recall that Hermitian, the matrix, the Hermitian means that I take the transposed and then complex conjugate, or that's equal as taking the complex conjugate and then the transposed. So now, given any n, I can compute any DFT matrix that I want of size n by n, and it will always be unitary. So this means all these columns are orthogonal to each other. Now, the DFT and IDFT operation are unitary transforms of vectors, and there exists a very efficient implementation called FFT or IFFT. This stands for fast Fourier transform, which has a complexity of n log n. So you can imagine that if the standard FFT has a complexity of n squared, n log n is much smaller than n squared for large n. And now here the book gets a bit confusing, but I will follow the notation of the book anyway. So suppose you have a vector x of length big N, and this is one entry here. The DFT of this vector is another vector of length n, and we call this capital X. So I think a more appropriate notation would be that you say that x0 till xn minus 1 transposed is the DFT of a vector, and then with small x's, x0 till xn minus 1 transpose. And the same for the IDFT, because the DFT and IDFT operate on vectors, not on individual scalars here. So this is the notation from the book. It's a bit confusing. What it really means is this. And now DFT is actually a linear operator, so you can write it in this notation here. And again, the notation is confusing. So here, this is a vector, and I call this big X in bold, and this is a vector, and I call this small x in bold, and their relation is just multiplication with the matrix Q. And why I say you should be careful, this is an n by 1 vector, this is an n by n matrix, and this is an n by 1 vector. So this means that the use of bold capital letters will sometimes be used for matrices and sometimes will be used for the Fourier transform of vectors. So you should be really careful in this lecture that you keep them apart. To make things even a bit more challenging, it turns out that in MATLAB, the notation for FFT and DFT, for FFT and IFFT, is slightly different because of the square root of n's that are in different places. So in the book, we define the DFT matrix with 1 over square root of n here, and then in MATLAB, this 1 over square root of n is outside of this DFT. So just be careful when you use them in MATLAB. They're not exactly the same as the mathematical symbols here. Okay, and here I say again, you should be careful with the DFT of a vector and a matrix. They are not the same thing here, even though they use the same notation. So now we will see why we care about this DFT. So we first revisit our circular and tuplets matrices. So let's suppose that we have an input here of length 5, a channel of length 2, And then the output will be of 5 plus 2 minus 1 will be of length 6. Let's see if that's correct. Yes, of length 6. So you can try this yourself by computing the convolution of x and h. You will find y. And you can write this in the standard now vector matrix notation. So you have a vector here of length 6, which is y, a vector of length 5, that's the input, and then you have your channel matrix here. So this is the H is the channel matrix. And in this channel matrix, you see the channel itself appearing, for instance, here, 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 and here. And this channel matrix is, well, in this case, will be a 6 by 5 matrix. If I now change the setting and make the input periodic, so I have period 4. So on the left side, the input was basically 0, 0, 0, 0, all zeros, and then 1, 1, 3, and then again all zeros like this. So that's what this input was. Here, you can assume that the input is 0, 1, 1, 3, 0, 1, 1, 3, and so forth, infinitely long. Channel is the same as before, but now the output will be periodic as well with period 4, which you can verify. Then you have your input as a vector, output as a vector, and again the channel matrix, which in this case is a circulant matrix, right? Because each row and each column are a circular shift of the previous one. On the left side, in this tuplets matrix, this is not true for this first row. You see this? The first row is different, the last row is also different. Sometimes you also see this in the columns. So what is different for circulant matrices is that they are square. Here they're 4 by 4. And we will see in the next slide now the relation between the circular matrices and the DFT. So it turns out that the DFT, let's see, the eigenvectors of circulant matrices are the IDFT columns. So we can now try to prove this. I think this is the most mathematical part probably of this lecture. So suppose that you have your standard model as before. Y is h times x. We don't consider noise here for now. So x is the input vector of length n. H is a circulant channel, n by n. And y is the observation of length n. Okay, and the first row of this matrix is, of course, the channel. We then introduce these vectors here, and this is one column of the IDFT matrix, so because it has a positive sign, if we go back, the DFT matrix has a negative sign, the IDFT is the complex conjugate, so it will have a positive sign. So this is a column of the IDFT matrix, a column of Q Hermitian. Then it turns out that when I multiply the channel matrix with this vector Qi, I obtain a scalar times Qi. So this means that Qi is an eigenvector of H with corresponding eigenvector value lambda. The way that you prove this is you look at one entry of this vector. So this is a vector, and then the mth entry is this one. Mth entry in this vector. I just write it with this notation, so I take the vector and take the mth entry, and by definition, it will be given by this expression. Right, so I multiply 1 over, this is the 1 over square root from here. These are these exponentials, and then I pick the correct values in the H matrix. Right, and I use the fact that it's a circulant matrix. I now write out this expression, so the first term is for n equal to 0, so H minus m times 1 and so forth. I now pre-multiply with e to the power j2 pi im over n and its complex conjugate, so this cancels out. And then I take this one and I multiply each of the terms with that. Oh, sorry. And then I obtain this expression. And now if you look at this closely, you see that this is basically the multiplication of the first row of the matrix times Qi, where I just rearrange the terms, right? So it's a sum where I just start first with the mth term and then the next one. So if I rearrange this, I obtain this. And of course, this square root of n goes back into Qi. So it then follows that this is true, where this eigenvalue has to be this product times the square root of n, right? Because I need to multiply and divide by square root of n to get Qi here. Right, so now we've seen that this holds true. So then what can we further deduce from that? First of all, if we stack all these eigenvalues in a vector, then of course this has to hold, right? So lambda is square root of n q times h because of this relationship. And of course q times h is the DFT of h. So this vector of eigenvalues is square root of n times the Fourier transform of the original channel. So that's one outcome from the theorem. A second one is the following. Now if we concatenate all these q vectors into the matrix form again, so we know that Qi is the ith column of Q Hermitian, so we concatenate them all again. We make all of these eigenvalues into a big diagonal matrix, then this relationship must hold. Right, so because h times the first column of this will be lambda 1 times the first column of this guy. Okay, so if this holds true, then I can multiply on the left side. Sorry, something is wrong. Something is wrong. Right, so this turns out to be not correct. The lambda should be here. Okay, now with this correction, then I can multiply both sides with q. So I multiply everything with q. Well, I have to decide on which side I multiply. Multiply everything with q on the left side. Then I find q h q Hermitian, which is this thing here. And then q times q Hermitian is identity. So this is a diagonal matrix. So what we've done now is we find a way to diagonalize a circulant matrix. Good. So how do we use this property? This is then the kind of last part before we really can explain OFDM. So you remember that in continuous time, we had the fact that a convolution time domain becomes a product in the frequency domain. In discrete time, we have a similar relationship, which is that the circular convolution in the time domain becomes a pointwise multiplication in the frequency domain. And to see this, we recall first this eigenvector-eigenvalue relationship. We've also seen this relationship here. And now we will use these relationships in the following sense. So this was our original observation model. Y is a circular matrix times X. We multiply on the left side with Q. And then we say that X is Q Hermitian times the DFT of X, right? So that is by definition, because X is defined as Q Hermitian times X times small x. Then we obtain this relationship here. And now this is a diagonal matrix. There's this lambda matrix, which on the diagonal, the Fourier transform of the channel itself. So what does this lead us to? This is now the key point. The circular convolution in the time domain becomes a pointwise multiplication in the frequency domain. So if I take the frequency transform of X, the frequency transform of the channel, do a pointwise multiplication, I obtain Y. So sometimes mathematically, this is denoted that the vector Y, okay, and this is the n by 1 vector, is given by square root of n, the vector x, again n by 1, and then this circle with a dot, which stands for pointwise multiplication, times the vector h, again n by 1. Okay. And now recall, h is the Fourier transform. Now this is a bit confusing, because now h is the Fourier transform of the channel, and it's also this matrix, so we have to be a bit careful. Yeah, you just have to be careful and make sure that you know which one is which. So this h here is an n by n matrix. Good, time for another break.